We're going to do one, maybe two sections. We're going to cover section 3 from chapter 4, and if we have time, section 4 as well. Section 3 deals with monotonic functions and the first derivative test. What we're trying to do here, the whole objective of this chapter is so we can draw accurate graphs of any type of functions that we're given. What we know from algebra and what we've done so far in the first or second derivative tests, which is what today's topic is about. So, to begin with, what is a monotonic function? Monotonic function is a function that is either increasing or decreasing on an interval. It can't be both. So, on a certain interval, a function has to be either increasing, decreasing, or 0. What does it mean if a function is increasing? What does it look like? Function is increasing if for every x values, x1 is less than x2, then f of x1 is less than f of x2. That says is what x's as they go from 0 to infinity. Let's look at those. We know that the y values are also getting higher. So the graph is increasing. Function is decreasing if for every x, x1 is less than x2, then f of x1 is greater than f of x2. So if here we have x1 and here we have x2, f of x1 is less than f of x2. Likewise, if it's decreasing, here's x1, here's x2. F of x1 is greater than f of x2. That, by definition, is what we're looking at here. How does this relate to what we've been dealing with? First derivatives, second derivatives. If a function is increasing, what do we know about it? Besides the points, what else can you tell me about it? If a function is increasing. What's the slope? The slope is positive. The slope is greater than 0. If it's a decreasing function, then the slope is negative. Why do we use slope? Well, how does that relate to what we're talking about? Exactly, because the first derivative is the slope. So what this shows us that in our functions, if the first derivative is greater than 0, then that's an increasing function at that point, at that interval. If the first derivative is less than 0, then it's a decreasing function in that interval. Where does it change? Can it change from positive increasing to decreasing function? If so, where does it change? What's that? And where is that called? Yeah, at f prime equals 0, that's the vertex, where the slope is 0. If you had this graph, this is f of x, the graph of f of x. Algebraically, what can we find from our algebra courses? Find the intercepts. How do we find the intercepts? Good answer. Find the x-intercepts of a function. Not x equals 0. Set the function equals 0. Anywhere the function is equal to 0, those are your x-intercepts. So what else can you tell me about the original function itself, about f of x? You can tell me the degree. Yeah, that tells us the shape of the curve and the end behavior. We can look at the degree of the polynomial. If the degree is even, what do we know about the graph? Yeah, both ends point in the same direction. If the degree is odd, then it's either an increasing function or a decreasing function. One more big thing it tells us. Yeah, you're right. The degree also tells us that. It tells us the maximum number of vertices we can have. It tells the maximum number of intercepts we can have. Because the degree also tells us the maximum number of intercepts, solutions, and vertices. The number of vertices is usually n minus 1, whatever the degree is. So tells us, the original function also tells us the y-intercept. How do we find the y-intercept? Set x equals 0 and solve for y. That'll tell us the y-intercept. We already have that much known about the graph. And that all comes just from the original function. Can we learn from the first derivative? It tells us where the function is increasing, decreasing, or 0. How can it do that? How can the first derivative tell us where it's increasing, decreasing, or 0? Yeah. If the first derivative is positive at whatever x you pick, on all x's in some interval, I is some open interval AB, A is equal to, not contained in. I is equal to some open interval AB. If the first derivative is greater than 0 for all the x's in an interval, then the function is increasing. On that interval. If the first derivative is negative on all x's in that interval, then the function is decreasing on that interval. And if the first derivative equals 0 at some value c in that interval, then the function has a vertex. Now let's think about this. When the first derivative equals 0, y is 0. Does 0 have a sign? No. But if you think about it, one of 3 things can occur. Actually, one of 4 things. Here's three functions. This interval, from negative infinity to 0, what's the first derivative doing? Is it positive or negative? What is the graph doing there? Is it going up or down? When do you read graphs? Which direction do you read them? Left or right? So this graph is increasing. As x gets larger, this graph is increasing. So the first derivative on this side is positive. At 0, the first derivative is 0. It has no sign. And on the right-hand side, the first derivative is less than 0. So at 0, in this first picture, at 0, there is no sign. The first derivative is neither increasing nor decreasing. We call this value the critical value point. Or some just call it the critical point. What happens at the critical value, or the critical point? At that is where the first derivative changes signs. Used to be positive, now it's negative on both sides of this function, or that one point. In the second one, you go from negative infinity to 0. What's the first derivative doing there? Is it positive or negative? It's negative because it's going down. the graph is going down as we read left to right. And we always read left to right. This side is going up. This side is going down. At 0, we have our first derivative equals 0. And then the other side, the first derivative is positive because the graph is going back up again. So far, so good? Let's look what's happening here. Now, in the first example, we have a decreasing function, and then we have an increasing function. So what do you think that makes our critical value, our vertex? Is it a maximum or a minimum? Are you asking or telling me? Yeah, it's maximum because if it's on the left, if it's increasing on the left and decreasing on the right, that means it reached the top of the hill. It's a relative maximum. It can also be an absolute if that's the entire function. But remember, our intervals are only subintervals. This could be one small part of a larger graph. In the second one, we have a negative slope, and then it turns into a positive slope. So if you're going down and back up, then we have a relative minimum. Now the next two examples are pretty much dealing with the same thing. If we have a specific point, is it possible to have a first derivative being 0 and it being positive on both sides? First derivative at that point is 0. Left of it, the first derivative is positive, it's going up. And then on the other side, it's also going up. Conversely, you can also have it going down. This is all we've done just by looking at the basic algebraic stuff and the first derivative. So, let's look at an example here. You need back up there? Okay. Example 1. A. Find the critical points, critical value points, of the function f of x equals x cubed minus 12x minus 5. B. Identify the interval where the function is increasing let's find the intervals and decreasing. So the first one, what is a critical point? What is a critical point? Well, the sign changes, but how do we find, mathematically, how do we find it? You're right, it is, but where the first derivative is equal to 0, which is exactly what it's doing, because it's the vertex. It's where the signs change. Okay. So we have to find the first derivative of our function. Once you find the first derivative, then what do? Set it equal to 0, because you have to set the first derivative equal to 0. Solve for x. Move the 12 over first, divide both sides by 3, and take the square root of both sides. So your answers are what? Plus or minus 2. Whenever you take a square root of something squared, you always have to put that plus or minus in front of it. Those are your critical values. These are the x values where your vertexes are. So we have negative 2 there, and we have positive 2 there. We know the first derivatives at those 2 points are going to give us zeros. So now, how do we determine where it's increasing, where it's decreasing, and how will we do that? For example, what's happening between negative infinity and negative 2? What's happening there? This is our interval. Negative infinity to negative 2. What's happening there? Well, what you would do, well, again, you can't guess in mathematics. You have to have either a theorem, a postulate, a proof, or a value to verify what you're saying. You notice we have a closed interval. We cannot use the endpoints. Because what happens at negative 2? It becomes 0. So we have to use 0. So let's pick a point that's not at the endpoints. Let's pick a point somewhere in that interval. And plug it in our first derivative. We have 3 times negative 5 squared minus 12. And work it out. Negative 5 squared is 25. 3 times 25 is 75. Minus 12 is 63. Since we know that negative 2 is a vertex, everything to the left of it will have to have the same sign. Since this is positive, what's happening on the left side? It's greater than 0, so it's increasing. We know the graph on the left side is increasing. At negative 2, it's 0. What about the next thing? Where's the next interval? Negative 2 and 2. Pick a value from there. If you can, always use 0. 0 is always an easy number because it gets rid of your x's. So we get negative 12, your first derivative. It's negative, so it's decreasing. That in that interval, it's decreasing. Pick a point between the last interval, which is from 2 to infinity. Okay. Plug that in our first derivative. Get 63 again. Because no matter whether it's positive or negative, when you square it, it becomes positive 25. So we're going to get the same value for this case. It's greater than 0, so it's increasing again. We know that the graph's increasing, decreasing, and increasing again. Well, we kind of knew that from our original function. It's a cubic function. The graph of x cubed is that. We know that our y-intercept is at negative 5. Do we know where the vertices are? The locations of them? Now we do. Once we found this negative 2 and positive 2, plug those back in the original equation, you find the actual locations of the vertices. Algebraically, you'd have to find the x-intercepts. So then you'd have the x-intercepts, the y-intercepts, the locations of the vertices, and the shape of the curve. Then just pick some points and just plot them, and you're done. Let's look at another one. Let's go on for this. We'll do some more. The first derivative test for local extrema. To do this, let's see be the critical point. Of a function. Remember, all of these functions have to be differentiable. What does that mean? They have to have the first derivative. So in other words, that's horrible writing. Function is continuous and differentiable. At every point, are on some interval. Containing C. Remember, let C be a critical point on some function, continuous and differentiable function, where it's differentiable and continuous at every point in the interval, and in the interval, C is an element of that interval. function does not necessarily to be differentiable at C itself. Why is that? Because remember, we have derivatives of functions even though if they have asymptotes. For example, the Atari function, 1 over x squared. So 3 things can happen. If f prime of x is positive, and changes to negative after C, then the function has a maximum, or as a relative maximum, which we call local. Why is it called local? Because it's related relative to that small subinterval where C belongs. So if the f prime of x changes from positive to negative, if it goes from positive to negative, then we have a local maximum. If f prime of x changes from negative to positive after C, then the function is I'll call it local then, local minimum. So if it's negative, then positive, and here's at C, then we have a minimum, a local minimum. If f prime of x has no change, then no local extrema at C. No local extrema exists at C. What that one says is we have this graph. It's the x cubed function. C could be there, but it's increasing on both sides. Therefore, you have no maximum, no minimum there. Likewise, if it's a decreasing function at C, there is no local maximum or minimum. All right, let's look at an example here. Example 2. For the function f of x equals x to the power 1/3 x minus 4. Find the critical points, the intervals where the function is increasing or decreasing. Let's see. The local and or absolute maximum minima. Let's take this. What's the first thing we have to do? To find the first derivative. So we can take these two and multiply them together. So we have multiply these two together. This is 1. So you add the exponents, you get 4/3. Distribute x to the power 1/3. Now we take a derivative of this function. 4/3 x to the power 1/3. 4/3 x to the power negative 2/3. We take out x to the power negative 2/3. What do we get inside the parentheses? What's going to happen to this one? It's x. This one disappears. What are our critical values? Where is the only way a function can equal 0? If the numerator is 0. So all you have to do is set the top equal to 0. Constant, so it doesn't matter. So x minus 1 equals 0 gives us x equals 1. That's one of our critical values. Another critical value is what makes the function undefined. Undefined is when 0 is on the bottom. So x equals 0 is our second critical value. We found the critical values. Critical values are at 0 and 1. So our intervals are from negative infinity to 0 to 1 to infinity. going to happen between negative infinity and 0? Let's pick a value. X equals negative 1. Where do we place the negative 1? In the first derivative. So this is our first derivative. Negative 1 minus 1. Negative 1 2/3. Negative 1 minus negative 1. Negative 1 minus 1 is negative 2. Negative 1 squared is 1. Cube root of that is 1. So our answer is negative 8/3. It's less than 0. So what does that mean? It's decreasing. Between 0 and 1. .1. So the first derivative at 0.1, 0.1 minus 1, 3.1 squared, then cubed. .1 minus 1 is negative 0.9. Bottom's going to be positive. So what's going to happen is the answer is going to be positive. We don't have to find the number. All we have to do here is find the sign. Is it going to be positive or negative? Guessing or telling me? Have you worked it out? The top's going to be positive or negative? Negative. Because you have 4 times negative 0.9. And the bottom can't be negative because the power 2/3 means you square it first and then take a cube root of it. So the bottom can never be negative. So this one's also negative. It's also decreasing. That's possible because remember, 0 is a critical value that makes it undefined. So we can't have two decreasing functions at one point. What happens between 1 and infinity? Let's look at 2. First derivative of 2. You can pick any numbers you want. 2 minus 1 over 3, 2 to the power 2/3. 4 times 1. 2 squared is 4. Cube root of 4. It's going to be positive, so it's increasing. Again, you guys can use calculators if you want. But all we're doing at this point here is, since we're looking for intervals where it's increasing, decreasing, that's all we're doing here is seeing if the first derivative at that point that we pick, the x value we pick, is going to be positive or negative. So, the interval from negative infinity to 0, function is decreasing. From 0 to 1, it's also decreasing. And then from 1 to infinity, it's increasing. Find the local and or absolute maximum minima. So our extrema points are at 0 and 1. When x equals 0, is this a maxima or minima? Or neither? Neither, because on both sides of 0, it's decreasing. So no extrema. X equals 0. When x equals 1, on the left side it's decreasing, so it's going down. On the right side it's increasing, so it's going up. That means it's the bottom, so it's a local minimum. Do we have an absolute extrema anywhere? This one has to be absolute, because look what's happening in the entire interval. From negative infinity to 0, the graph is decreasing, right? From 0 to 1, the graph is decreasing. So if it's always decreasing, that means at this point here, when it starts going up, this has to be the lowest of the entire graph. So it looks like something like this. So this is also an absolute minimum. Again, it helps when you see the pictures and what those intervals are telling us. So from negative infinity to infinity, it's decreasing, then it's still decreasing, and then it's increasing. So. Example 3. The same things. Here's your function. X squared minus 3 e to the power x. A. Find the critical points. Intervals where increasing or decreasing, and local and or absolute max min. Let's look at this. The first thing we have to do is find our derivative. Easiest way here, since it has x's on both of those, let's use the product rule. So this one is x squared minus 3. The derivative is 2x. E to the power x, e to the power x. We get e to the power x times 2x plus e to the power x times x squared minus 3. Actually, for this point here, we can factor out an ex, giving us 2x plus x squared minus 3. X squared plus 2x minus 3. Factor this one out. Second signs of minus have opposite signs. That means the bigger number is going to be positive. What times what is 3? When you subtract them, you get 2. 3 and 1. 3 times 1 is 3. 3 minus 1 is 2. Now we set this equal to 0. Take each of these terms, set them equal to 0. Can e to the power x ever equal 0? No, that doesn't get us anywhere. So x equals negative 3, x equals 1. Those are my critical values. Critical points. We go from negative infinity to negative 3, positive 1, positive infinity. So our intervals are going to be negative infinity to negative 3, negative 3 to 1, 1 to infinity. Those are my intervals. To find out where they're increasing, decreasing. So what value you want to pick? Negative 4. F prime of negative 4, e to the negative 4, negative 4 plus 3, negative 4 minus 1. Negative 4 plus 3 is negative 1. Negative 4 minus 1 is negative 5. The answer is going to be positive. That means it's increasing. Again, the actual point itself for this section, for this part, is not important. We just need to know, is it positive or negative? Let's use 0. F prime of 0. E to the 0, 0 plus 3, 0 minus 1. 3, negative 1. It's less than 0, so it's decreasing. E to the 2 times 3 plus 2, 2 minus 1. So it's positive, so it's increasing. So the graph's going to look like is this, then this, and then this. So at -3, what is it? Is it a maximum or minima? The local maximum, because it's the highest of that peak. At 1, it's local minimum, because it's the lowest part of that. And since these graphs go on infinitely both ways, we have no absolute maximum or minimum. So that's the first derivative test.